As I noted earlier, some naturally occurring discrete random variables have been studied intensively by statisticians over the centuries, and that is why we now have all these neat mathematical results that we can use to easily derive conclusions from these phenomena. So let's first look at the so-called binomial probability distribution. Please take a minute to read the 4 key properties. The way to think of this is we are doing n identical trials. Each time we hold a trial, there are 2 possible outcomes. One we call success, the other we call failure. This assignment is rather arbitrary. So for instance, tossing a coin, you could call heads success, tails failure, or the other way around. The third assumption is that the probability of success is denoted by small p. Remember, the value here should be greater than or equal to 0 and less than or equal to 1. But that probability does not change from trial to trial. And finally, the trials are independent, i.e., the outcome of each trial does not affect the next trial. So our interest in this is as follows. If I do n trials, what is the probability that I will get x successes? For example, if I try 9 times, what is the probability I will succeed 5 times, or 0 times, or 9 times, or 3 times? Another way to think of this is, suppose I toss a coin 5 times. What is the probability I will succeed 3 times, succeed in the sense of getting heads? So we can use the binomial probability distribution to calculate these probabilities. This is the formula for the binomial probability. Please take a minute to read the formula. Remember the notion of the factorial and exclamation point. So 5 factorial is just 5 times 4 times 3 times 2 times 1. Let's break down this formula. The first part is just the number of outcomes that provide exactly x successes in n trials. And the second part is just the probability of a particular sequence of trial outcomes with x successes in n trials. Let's try a concrete example. Evans Electronics has seen a turnover of 10% of its employees. Hence, there is a probability of 0.1 that a particular employee will no longer be with the company next year. So the question is, if we choose 3 random employees, what is the probability that one of them will leave? So in this case, what we are doing is as follows. Denote the probability of leaving as P. Hence, basically we are saying that leaving is success. And remember that there's a 10% probability or a 0.1 probability that an employee will leave. Hence, we can consider this outcome, for instance, 1 employee leaving and the 2 staying. Hence, 1 success and 2 failures. And if we tally all those possible outcomes, we can also compute the respective probabilities. So for instance, the first one stays, the first one leaves because success is leaves, and the next 2 stay. Or the first one stay, the second leaves, the third one stays. See, there are all these possibilities. And you can then calculate the probability that 1 person of the 3 will leave. But this is tedious, as I said. The nice thing is we can use the binomial probability distribution function, which is this. So all you do is you know that P is 0.1. You know that N is 3 because we're implicitly doing 3 trials. And we're calculating the probability of 1 success. So plug in those values into the equation and you'll get exactly the same number, which is 2.243. Hence, there's a 24.3% probability that one worker will leave. Now, please take a minute or two to try for yourself and compute the probability that 2 workers will leave or that 3 will leave. This is another illustration of solving the problem using a tree diagram. The ones that are circled are precisely the outcomes where only one employee of the 3 leaves. But to reiterate, it may not be convenient to use the tree diagram. It may be faster to use the binomial probability equation. Just to note, there are tables that one can use, but with modern calculators being very powerful, all you need to do really is memorize the binomial formula. These are the 3 properties that statisticians have established for the binomial probability distribution. These are the formulas for expected value and the variance, and of course the standard deviation is just the square root of the variance. Please take a minute or two to review these equations. Let's now turn to how to use these. Take note of the equation for the expected value. It's just equal to n, the number of trials, times p, the probability of success in each trial. So for Evans Electronics, the expected value is 0.3, which is 3 times 0.1. Hence, how do we interpret this? On average, 0.3 employees of every 3 can be expected to leave. And the variance of the number of people leaving is 0.27. And of course, the standard deviation is just the square root, which is 0.52. Here is a short test. Please take a minute to read this and think of the answers. Here is another test. Remember the coin toss example? Can you use the binomial probability distribution to compute the probability of getting 5 heads when tossing a coin 5 times?